anyone who's online. So if anyone attending virtually has questions, you'll just have to shout out because we can't see if you raise your hands. So we'd like to welcome Miguel Arratia. He has, many people know him. He's done a hell of a lot of things. I think overlaps with most everyone here, whether it's jet measurements at Atlas, looking at how to understand jet substructure and the H1 data, proton tomography at class, nuclear effects, a lot of those things and what can be done at the EIC, as well as detector-related work.
Don't forget his work on Alice.
And his work on Alice, yes, and many more, I'm sure. And today he'll tell us about something completely different, sort of nuclear effects on the spin structure of the proton, what can be done at JLab, as well as possibilities for the EIC.
Yes, thank you very much, Jim. And yeah, thank you for the opportunity to, yes.
Sorry, I didn't mind me to interrupt, but I also want to mention one of the latest round of early career award winners.
Thank you very much. Okay, so today I'm going to talk about some speculative ideas. Okay, so I hope you don't mind that. I'm going to throw you some ideas. Maybe we can bounce them around and get something out of this. Okay, that's my hope anyway. Okay, so this talk is about the proton, and in particular the quark and gluon structure of the proton that we all know and love. This used to be my favorite artistic impression of the proton. This is coming from an artist at CERN. It's lovely. But I have a new...
How come there are two red valence quarks there?
I cannot go back. Anyway, but artistic freedom, that's artistic freedom. But my newest favorite one is this one, made by people at MIT and JLab, where it's like a video of the quark and gluon structure of the proton. I love this, made out of visualizing the PDFs. And I just like to remind myself, anyway, that if we are looking at the energy dependence of the proton structure, we are really looking at the time in the fundamental sense. It's a time evolution of this quantum system, because of course those quantities are conjugates. So that's lovely, that's what we want. We have come a long way understanding the proton structure, but and there is still a lot to be understood, that's for sure. But in order to spice this a little bit, we want to add a little bit of salsa, if you want, to the proton structure. We want to study this when the proton is not free, but embedded in the nucleus. Okay, so we want to study those quantum phase density measurements that I mentioned before, but when the proton is in the nucleus. So the key question is really, how does the quark and gluon structure of the proton change when the proton is not free but bounded? So this is a picture that I made. I'm proud of this. Picture where you want to study the evolution of the quark structure of the proton, but when that proton is surrounded by other quarks and protons. I mean, that's kind of what is not seen here. It's not as if we want to understand this proton structure when it's embedded in the nucleus just per se, but rather because there are other quarks and gluons. So you want to understand how the entire thing is behaving in terms of quarks and gluons. And this, at least to me, this... Yes?
I cannot really mute it. Turn off the sound on the iPad.
This is a very ugly feature of the Zoom that in the tablet.
No, but on Zoom you can go without sound.
You might. No, it's a bug. It's a bug. I'm sorry, I cannot fix it. It's a bug in Zoom.
Problem, yeah.
Okay, so this is the question. You can find it in every summary paper or any long-range plan type of question. I like it because it has the word bound in there, and that's critical because we don't really fully understand the binding in terms of quarks and gluons. And it would be interesting, perhaps, to learn about that, the process of binding. If we possibly understand the structure of the quarks and gluons of protons that are bound, maybe we can understand how the process of binding is happening in the first place. So that's the motivation. And we know that this proton structure changes when you have the protons embedded in the nucleus. We have known this for long time, since well before I was born, actually. And this is the EMC effect. This is some data that shows you the summary of EMC effects measurements more recently done at JLab and SLAC. So is this ratio of cross sections when you measure the structure function of a nuclear target like gold and divide that by reference, like deuterium. So this is the traditional shape that we have seen many times. I'm pretty sure you are aware of this, where there is a slope that grows. Well, the slope grows with a mass number, but there is a slope in particular in the region between 0.3 to 0.7. It's a pretty linear relation, which you can encode with the slope of the ratio, which is on the right-hand side. As a function of mass, it has like a weak dependence that you can fit linearly with mass number. And so there is a lot of data and there is a lot of measurements, but we still don't have a good understanding of what this means. There are many theories around, and those debates around those theories are quite heated and interesting. And of course, you have heard about this from John and collaborators. I will not go into much detail to say that it would be nice to have a different angle on this old question to try to steer things a little bit. So that's one motivation for the type of measurements that I will describe to you today. The second is the same experiment that gave us the EMC effect gave us the EMC puzzle, which was a measurement that the spin of the proton is not accounted by the spin of the quarks. Also, in the 80s, this is a famous plot that shows you that the momentum carried by the quarks just doesn't match up. And that gave us the modern view of the proton spin structure. Like before, this picture could have been right, but then after this measurement in particular, and following measurements at Rick and elsewhere, we have this much more refined and complicated structure of the spin of the proton. So what I'm going to ask to talk about today is an experiment that is going to basically mix those two things. You want to mix the EMC effect with the EMC puzzle. So you put a puzzle into a puzzle, a riddle of a riddle, and maybe something comes out of this. So the answer is, how does the spin quark gluon structure of the nucleon change when the proton is bound? So that's the new question. Now you add a spin to it. And so you have the spin structure, you can measure that, but now the proton is embedded in a nuclear environment. So how do you do this measurement in principle? In principle, this should be easy, but there has been no experiment doing this. And no experiment ever has searched for the EMC effect equivalent in spin structure functions. Even though the experiment in principle is naively at least, is simple. You have electron scattering of a polarized nucleus. And then in principle, you can be able to understand this. So in principle, it's simple. So why hasn't it been done, you might ask? Here I'm showing you the nuclear spin, at least for the main isotope, for every element in the periodic table. Most nuclei have spins, so they can be polarized in principle. So that's not an issue. You can easily polarize a target. Okay? It's not an issue, but it gets complicated. Why? First, like technically, it's difficult to polarize the nucleus, but there are techniques in order to do this. The technique, you may be familiar with this, is called the dynamic nuclear polarization. It's a technique that is over 70 years old and is the way that people have enhanced the sensitivity of things like nuclear magnetic resonance and stuff like that. So in many fields, you produce nuclear polarization. So in principle, even though it's difficult to polarize the nucleus, you can still do it technically. The way that is done is you polarize electrons, which are much easier to polarize, and then you transfer the spin of the electrons to the nucleus with different ingenious techniques. So in principle, it can be done. You can polarize a nucleus, but the problem is that you have immediately come into an issue, which is there is a trade-off. A wise man once said, there are no solutions, just trade-offs. and this is one example. If you increase the size of your nucleus, you're increasing the nuclear effects, right? That sounds obvious. You make this bigger and bigger, any nuclear effects are going to be amplified. But the spin effects, like the spin-dependent cross-section of a nuclear target, scales like 1/8. So you're basically essentially making the cross-section smaller and smaller as the nucleus grows. So you need a trade-off. You need a nucleus that is big enough to give you a nuclear effect, but not so big as to dilute the signal. It needs to be measurable. On top of that, the measurement needs to be feasible. So the material has to have the correct properties. And in the experimental world, you would like to have control over this with high accuracy. So this is a list of possible solid targets, and in particular focusing on small ions or nucleus. So you can do measurements with lithium or boron or carbon or fluoride in principle with different molecules, compounds. These are in particular solid targets, which are easier to do for use in experiments. Lithium-7 is a great example, or is a great candidate because it can be polarized to over 90%. So technically, you can polarize lithium-7 using this technique that I mentioned to you before, and you can polarize it to 90%. And that's actually very handy.
So this can be done in future ERC?
Sorry.
I mean, this can be done, 90% polarization can be done in the future ERC.
Yeah, I will come back to that point. Yeah, that's a good question.
Another point, how to understand 55% polarization? I mean, random just 50%. This is not correct, understand?
That's an excellent question, actually.
I think the 55% is for a proton beam.
Yeah, I will need to come back to you to that point. Actually, it depends on how exactly you define this, but yeah, interesting. I didn't consider that before.
But they're defined such that polarization is 0 if it's 50-50, right? So
yes. Anyway, lithium-7 has other wonderful properties. First of all, it's stable. It has a spin 3/2, and more importantly, the spin of the entire nucleus is carried in most part by a single unpaired proton. You can imagine this, or you can realize this by just looking at the shell structure of lithium and realize that all the protons and neutrons are paired except one, which is a valence proton. And with the shell model, you can estimate that the spin of the lithium is carried like 80 or 86% of the spin is carried by that proton. And you might say, or you might think, that the shell model is naive and is not complete, and you're right, but there are better ways to do that, and like with green Monte Carlo methods and other fancy techniques, and you end up with the same answer. So the answer is that most of the spin of lithium is carried by a single proton. So this is the wonderful experiment. You have lithium, you can polarize it, and it's just like having a polarized proton embedded into a nucleus, which is large enough to give you nuclear effects. So this has never been done, and we are going to do it.
So when you say embedded, it sits in a P shell, right? So it sits away from the center.
That's an excellent point. Yeah, that's an excellent point.
So don't you worry about that.
You should take that into account too. Yeah, I personally think that is an excellent point that we haven't explored yet. But all the models, calculations that we are going to compare with should and do take that into account.
So what is the typical density of this object? I mean, a shell model, you can ask this question. Right?
It's complicated because in particular lithium-7, you can think about this as an alpha and then other 3 nucleons.
Yes.
So it's not trivial. So the shape, I don't know what the shape is, but it's an alpha with some 3 nucleons around. So it has this alpha core. To what degree that impacts the measurements, I don't know.
So one doesn't know from these calculations what the average density is what is it, a proton out there?
I don't know. I don't know that number on the top of my head, but I would imagine that that number is known. I mean, you have the potentials and all of that.
Right.
That you can run those numbers.
Okay.
There's also fairly sure there's electron scattering data, which I could dig up if you give me enough inducement.
There is. I searched
And
for it.
so-
It's elastic though. Elastic.
Yeah, but that'll still, well, that tells you where the protons are.
Yeah, but this, I mean, but you want to have a shell model calculation where you know you have you go to Joe Carlson, he calculates you the best wave function you have, and then you ask yourself, I take this p-wave function and then average over the nucleus and see what the average
shell
is.
model Monte Carlo was.
Yes, exactly.
Or no core shell model.
Yeah, somebody should, I mean, that should
That
be, one should get a decent number, right?
Yeah, but you could also compare that, if you want to know the density, you need to know the size, and you can get that from
Yeah.
electron scattering.
But it's not only the size, I need the density where this with this fellow tests.
Right.
Right? If this guy sits out there in a halo nucleus, the
Right.
experiment would be totally useless because the thing sits out there away from the nucleus, from the rest of the.
We're in the process of calculating that for a bunch of light nuclei, not
Okay.
for the polarized, but we can do it, and we're separating
Very good.
proton versus neutron.
Yeah.
But just for reference, if you look at the unpolarized, so helium-3, of course, has a very large radius, very dilute nucleus, and it still has about half of the EMC effect of carbon. So it's not, being very dilute does not have as much of an impact as you might expect. And I'm sure we'll see calculations for the spin structure here.
Just thinking on the fly here. If that is the case, like the spatial distribution of this, like this proton is flying around somewhere else compared to the other protons, you might be able to pick that up with some observable that is sensitive to that. Not inclusive of scattering, but something more complicated. Maybe we can discuss that in the context of things that I will discuss a little bit later. Well,
Can I ask
Yes.
a quick question?
Yes.
Yeah, I'm Miguel. Actually, related to John's remarks. So you showed at the outset the compendium of EMC effects as a function of A. Is lithium among them, and where does that sit?
I think there is lithium in that. John might correct me if I'm wrong.
The data exists, but it has not been analyzed yet.
Yeah.
So, right, so we don't, yeah. So
Yeah.
is it known to follow the systematics? I mean, okay, it hasn't been analyzed, so you don't know. Be interesting whether it follows the systematics or whether it's an outlier because of its proton sits in the P shell and so on. Yeah, that's a question.
All right. Okay, so this experiment will be run in Jefferson Lab. I'm sure you know that this was upgraded in 2018. We have a high energy, high luminosity electron beam with energy up to 11 GeV. So what is the second ingredient is a complicated target that you can see in here. But the important thing is that this exists and is running, has been used in different experiments, and it's a target system that allows you to longitudinally polarized solid targets. So you put your target in a cell that looks like this, and into this system, and there all the complexity of running a polarized target is there, all the diagnostics and all that is running, and this lithium experiment is just going to use that. So we only need, quote unquote, only to put lithium-7 in this capsule, and then everything else is done. There's a happy coincidence here. This is completely outside the field that I'm describing, but it's interesting. So for completely different reasons, Jefferson Lab is working with people doing fusion, like nuclear, like energy fusion, like Tomcat, or whatever the name they are. Because polarized lithium-7 deuteride pellets are useful for that. Why, you might wonder, and is because the cross sections for fusion go up if you polarize a target, allegedly. And they're going to produce this target and measure polarization and then run that in a fusion experiment. So this year and next year, Jefferson Lab is just making exactly this, exactly what we needed for completely orthogonal reasons. But the point is, we are going to get, very easily lithium-7 deuteride pellets that can be polarized. It's very technically difficult. You have to irradiate the material in order for it to have the magnetic properties you need in order to polarize it. Anyway, there is a lot of work going on. So we got the target. There is a second happy coincidence, which is if you go to the Jefferson Lab schedule in 2026, there is an experiment that is going to run with longitudinally polarized targets, which is the one that is using the target that I mentioned before. So this experiment already ran, but it's going to finish running the second half of their data taking in 2026. And because of that, because we are using exactly the same target, we can just get into the schedule. And that's wonderful, because this was in principle many years in the future, but now all of a sudden, because of this fusion thing, we get in the schedule very quickly.
So can you do transverse polarized?
So this is ammonia. So they do basically longitudinally polarized protons, and then longitudinally polarized neutron.
We can do transverse polarized.
You could do, but with a different target system, and it's more complicated. Longitudinally polarized is easier. Good. So the detector that we're going to use for this is the class 12 detector in hole B. This is the diagram. This is where you put the target. The electron goes from left to right. It's a large system. You can kind of guess it from the picture I show you on the right-hand side that shows some members of my group visiting there. And it's a large detector. We can measure basically all the kinematics in the fixed target mode. You measure the electrons and whatever else comes out of this experiment. So this is a kinematic coverage for class 12 with an 11 GeV beam. This is the experiment we want to do, electron scattering of lithium. And this is the X and Q squared diagram, the acceptance basically. So we are going to cover, not surprisingly, because all Jefferson Lab experiments in hole B measure the same thing, the balance region, but now with a Q squared ranges from 1 to roughly 10. So that's the measurement that we have. And so that's a very interesting kinematic.
Can you go to the small x below 0.01, which is CGC?
Just barely. Like I think the kinematic limit is, I don't know, you barely get to 0.1, a little bit. So you might be able to see a little bit of anti-shadow.
So we're asking 0.1 or 0.01?
0.01.
0.0, there's no way. Below 0.1, yeah, we can. Like 0.05 or something like that. Anyway, so this is the expected results. This is not the previous plot, but I didn't bother remaking this. This is from the original proposal, which was 10 years ago. So the expected results for this observable, which is the difference in cross sections, which is sensitive, which is basically measuring G1 for lithium and the proton, is this. So the error bars are the expected statistical uncertainties, which are going to dominate over the systematic uncertainties, which are little bars. Different colors are giving you different Q-squared ranges, and the curves that are in there are different models. And there is no data for this, so the models are all over the place. Okay, you can have these huge bumps in this particular model. There is another model that has no X dependence, whatever. I don't want you to get distracted by the models, because the models are not worth very much since they haven't been tested with any data yet. The important thing is that this data is going to be able to constrain them and hopefully answer some of the key questions that we want to answer, which I will come back to later in one slide. Let me just give you the second piece that you can measure. Rather than the single spin asymmetry, you can measure double spin asymmetry in lithium and in proton. And these are the projected uncertainties for that. So the error bars, again, the projected error bars, the points are located in a random place or like an arbitrary place. And the models predict different things again. And the important thing now is that the data is going to be able to discriminate between all these models. And you might wonder, well, what's the point? Well, the first point is that we're going to kill a lot of models. That's good. So Saint depth is coming from most of them. Some of them might survive. But the important thing is that there are broadly speaking, there are two categories of models. One, that try to explain the EMC effect. One is like a mean field type of approach, where all nucleons are modified somewhat. Whereas there are another category of models, which are the short-range correlated models, or correlation models, in which a subset of those nucleons are modified a lot. And those different categories of models predict different things. In particular, as far as I understand, John, you might correct me, the short-range correlated models predict very subtle or no effect on the spin effects for this measurement. Whereas other models that are like mean field approaches, they predict larger deviations. So these things that are in here are the equivalent or the analogous of the EMC effect with polarized. I don't know about you, but I find the term polarized EMC effect to be a mouthful. So whatever we find, I'm going to rebrand it as the class 12 effect. I hope you take it. Because we need a rebranding that has been over 40 years. So in the spin case, we don't know what we are going to measure. We're going in a fishing expedition. But that was the inclusive DAS. The beauty of the class experiment is that you can measure not only the scattered electron, but hadrons. So what I want to present to you now is what we could do to broaden the program. So we not only inclusive DIS, but we can do semi-inclusive DIS with one hadron in the final state or with two hadrons in the final state. So by analogy, this is now probing cities of a polarized proton that is bound in nuclei. Why do we want to do that? It's a complete fishing expedition. As far as I know, there is no data. As I mentioned, if there is no data in inclusive deep inelastic scattering, of course there is no data in cities. So we're just going to find something. And as I told you before, we're going to call that something class 12. And we're going to spend decades thinking what is that. But the semi-inclusive deep inelastic scattering is an interesting probe because it allows you to go beyond the one-dimensional picture or one-dimensional structure of the proton to a three-dimensional picture. In principle, if you measure the lepton variables and the hadron variables, you are sensitive to the 3D motion of quarks and gluons inside the proton. So that's like the canonical regime or the canonical measurement that people have done in order to prove this, transverse momentum dependent PDFs. In the unpolarized case of cities, this is the measurement that we typically do. So we basically do a ratio where we count hadrons and we divide the cross-section by the inclusive electron scattering cross-section, and we repeat the same thing, but now dividing by a reference, which is typically deuterium or a proton. So we do this measurement, and this ratio is not unity, that is, can reflect nuclear effects.
Sorry, Riverside is also polarized?
No, this is the unpolarized case. So this is what we typically measure just in unpolarized. I'm going to show you what we have learned from unpolarized, and then what we might project for lithium case. Okay, there are a few reasons why I wanted to show you this. One of them is that we did these measurements for the unpolarized case, and this is like 6-panel figure illustrates what this ratio is as a function of PT, transverse momentum, of the hadrons with respect to the photon. Different colors illustrate different targets. We have carbon, iron, and lead. And you see a deviation from unity, which is evident, and a very interesting pattern where large PT, you see a large enhancement in the nuclear case. So you see much more high PT hadrons in nuclear cities than in the proton cities. People more clever than me, took that data and other data in a global fit, in a QCD framework that is factorized, and they concluded that quarks nuclei are more broadly distributed in transverse momentum than in a proton. So this, as far as I know, was the first time that people have looked into the bound structure the structure of the bound proton. But this is like a two-dimensional EMC effect, if you want. You're studying this ratio as a function of x and as a function of the pt of the quarks. And this is just one example in which we are moving towards a multidimensional picture of the proton. And I am hoping that if we were to repeat this type of measurements, but with a bound polarized proton, we might learn
Can
something
you
else.
go back to the previous slide?
Yes.
The what? Yeah. I see here GBUU.
Yeah,
If this is what I think it is,
yes.
I mean, this is just a stupid hydraulic transport code and it seems to fit your data right on. So how can I, if this works, how can I then make stories?
That's an excellent point. That's an excellent point. Yeah, what I can tell you is that I didn't bring this.
Yes.
This analysis is using a completely different picture. They also fit the data.
All right.
So they claim that they can extract.
But GBU is just rescattering and that's
I know,
it, right? So,
I know,
okay.
it's a cascade Monte Carlo model.
Yes.
And it fits the data well. So we have the situation where
All right.
we have different competing interpretations. I give you one, but I could have
Diplomatic way
given
of saying
you. Well, that's the only way that I can. We should discuss a bit later that because I would love to have an observable that I can pin down these models and then distinguish between them. But let me just give you the expected nuclear effects of lithium-7. I don't have any model that is allowing me to predict what the nuclear effects, by nuclear effects, I just mean deviations from unity that are going to be lithium-7 that is polarized. I don't have any model, Monte Carlo or otherwise, that allows me to do that. But just for reference, what are the nuclear effects that this given model predicts, which described the data before for lithium-7. From the experimental point of view, we care that this measurement is going to give us something that is not a null result with the systematic and statistical uncertainties we expect. And that is the case. So we expect uncertain effects that are between 5 to 10%. So this goes back to the point that we want a nuclear target that is heavy enough to give us some nuclear signal, but not heavy enough. I will give you a point in a second, Spencer. We want something heavy enough to give us a signal, but not so heavy as to dilute anything else. Spencer.
So, I mean, the thing we're wondering about is when you have polarization, that can change the kinematics. You know, like you may have cases where you enhance you have polarized target, you enhance pion production in one place and reduce it in another. So
you mean by the underlying quark distributions?
Yeah. So how do you how do you account for the difference between these expected effects versus I'm not sure what the right collective effects or effects because you're in a heavy nucleus?
No, that's an excellent question. I don't have the answer. I don't have a model that allows me to put the known helicity distributions, run some calculations, and give me a spectra of times. I don't have it. I would love to have that. I don't think that any Monte Carlo exists. There might be a way to compute this from a factorized formula, and we could do that in principle. Although it gets very nasty very quickly because if you want the city's case to get a prediction, you also need to convolve the fragmentation functions. And those in principle, I guess, are also spin dependent, and it's going to get very, very nasty. Mm-hmm. So the interpretation of these measurements is not going to be easy, I take that for sure. But the way that I am looking at this, and I think I stressed that point before, I think this is from the experimental point of view, we can define very well the observables that we're going to measure. We are going to be able to measure them very well. And that's why I call that fishing expedition, because who knows what is going to come up, and there will be lots of homework from the theory point of view about what we could do. Let me just continue to show you what we could do. Another more complicated final step, just to make it even more complicated. you can do dipions. And we've measured this. And when you look at the two pion correlations, you see these functions that are like Gaussian centered around pi. And when you go to nuclear targets, which are shown in different colors, these correlation functions get wider. In particular, we compared this with a bunch of models just to go to your point, Volker, not only to give, but also other partonic models like e-hydrogen, and they also describe the data to different degrees. So this is the differential cross-section of the dipion correlation. We took the width of the curves that I showed you before. So you have this, but in bins of different variables. In particular, when you bin this in the transverse momentum of the secondary hadron, you take the widths. This is how it looks like for deuterium, carbon, iron, and lead. And 3 different models are compared to the data. Gibel, which is a hadron model, e-hydrogen, which is a partonic model, and Beagle, which is something. I don't know how to describe that. It's like a mixed bag of different things. And at least in this observable, we are able to, at least qualitatively, discriminate between the models. You can see this is the width of the cross sections, and this is the difference between the widths in the nuclear case with respect to the proton or deuterium case. Some models are predicting an increase with PT, others slightly worse or a slightly weaker increase, and other is predicting a decrease. And obviously the data is not favoring the blue one, which is the e-hydrogen case. In this case, it's if anything closer to the green, which is the Beagle, which is a Pythia-based nuclear effects type of Monte Carlo event, which was actually described, invented for the EIC, and for some reason is making a reasonable prediction in these kinematics. Okay, so that's the type of measurement we could do, and you can throw a spin into it.
Can I ask a question about that slide?
Sure.
The previous one?
Yeah, sorry, I didn't see your hand.
Yeah, no, that's okay. So it looks like, the ratio is quite interesting, right? But it looks like the slope in the red, except for when you get to the lead, and nobody gets anywhere near the lead. I wonder, is that because it's, why is that?
The slope, I mean, I see it like the slope.
Right, the slope with PT squared. Oh, sorry, the slope with PT.
In the first row and the second row?
The second row, the difference.
Yeah, no, you're right. You're right. The data is showing no slope or consistent with no slope or a weak slope at best.
Right.
And the other ones are predicting the slopes in different signs. Yeah, you're right.
Yeah, but for lead upstairs, the peak, whatever the key BUU seems to be at all 3 points. So why is it missing in the ratio?
Well, this is because that's a good point. This is, first of all, it's a log scale, and this is a linear scale, so it's difficult to gauge. But second of all, this is the cross section, and this is the difference of cross section. Like this is the sorry, not cross section, width difference. Yes. So in this case, this model, the reference deuterium, is not fitting that very well. So when you take difference,
deuterium, okay, got it.
Yeah. So it could be in the deuterium model. Okay. We used this Gibu model again to predict what type of nuclear effects you expect for a lithium target. This is for the unpolarized case, but just to give you a flavor of the type of effects we expect. And again, they are at the 10 to 5% level, which are measurable, at least with the precision that we have. So now we will just go in our fission expedition and see what we see if you throw in there spin. If you throw away a spin, you might be able to do interesting analogous measurements of what people have done before. I will show you in a second. You can do beam asymmetries or target asymmetries. Okay, we know from data from class, recent data. This is a paper in 2013 that if you do a beam spin asymmetry. So you change the helicity of the electron beam. Something like that. You can correlate in that hadron measurements. You can measure a leading hadron, like high energy hadron, and then you look at other hadrons in the event and see how they are correlated. They found, perhaps it was to their surprise, as I know, because they're my collaborators, but perhaps it's not entirely surprising. An entanglement between the polarized quark and the proton remnant. So why do they say that? It's because they measure a pion that presumably came from the struck quark, and then they look backwards and they observe a correlation between that pion and the hadron going backwards, which presumably comes from the hadron remnant. Okay, and so it's a huge signal that they can easily measure, and it depends in a way with PT that the asymmetry is negative and grows in magnitude when you go to higher PT. So that's what they claimed, and we could do similar measurements, but now instead of having a proton target, we can have a nuclear target, and that's like something we were thinking to do anyway with experiments that are not lithium, and this is a projection with experiments that are not lithium. So because this is with the target that is unpolarized, the data is in black, the data that I showed you before. Here, this is real data proving the entanglement between the polarized quark and the proton remnant. And you can throw in there now have a nuclear target in there, so the remnant is way more complicated, and we expect to be able to measure this effect if it is there. So we don't know whether the asymmetry will go away, or it will stay, or go bigger or smaller. Again, this is one of the type of measurements that whatever we find is going to be interesting by definition, or at least by my definition, because we don't have a clue what is going to come up. So that's for the spin asymmetry with the electron beam, but we can do similar measurements, but now with polarizing the lithium target. So that's another type of measurement we're going to do, target spin asymmetries. And we are going to measure them for the first time, and who knows what is going to come up. So that's a message basically across the board. We're just measuring things for the first time and seeing what sticks.
So you polarize, can you control the JZ component?
The JC.
J direction and the projection on the Z axis.
The X and the Z axis.
The JZ value, for example, deuteron has a JZ.
The deuteron, I'm not sure what you mean. We have this, well, it is true that, yeah. So you can polarize lithium.
Yes.
But now, well, it's complicated because then there is a compound that has lithium-7 with a deuterium around.
I mean,
So is that what you're asking?
you
No.
have polarized, but you have different JZ component or JZ value.
You mean the helicity?
The angular spin projection to the Z direction.
Yeah, but that's what we know, like event by event, whether the lithium is polarized this way or the opposite.
For example, this way. Maybe
Yeah.
you could discuss it.
Yes. Okay, thank you. Good. Okay, let's move on. So actually, what I'm hoping is that whatever we find in the class 12 effect, we're going to carry over with the EAC. EAC has the capability in the baseline design, or at least the traditional design. I don't know whether it's in the baseline or not at this point in time. But you have polarized electron, protons, deuterons, and helium-3, so up to A3. There is a huge program that you can do with all of those. You can study the neutron spin structure by using helium-3 as a polarized neutron target, or you can study deuteron structure, or you can do tagged cross-sections on a deuteron and get neutron targets. And I will not go into much detail, but there is no plan, at least now, to do something even more heavy than helium. That might change though. I was just checking recently some slides by Chao Peng from Argonne, and I realized they are actually working on a lithium source. It's becoming quite real, actually. They have an LDRD and other sources of funding, and technically it might be possible to do it if they're working on it, I assume. So we might have a lithium-7 beam that is polarized in the EAC. So that would be interesting, and of course, higher energies at the EAC, but allows us to probe whatever we find at lower X. That's my hope, anyway. So now I will move on in the few minutes that I have left to talk about some EAC measurements that we're going to do in the future quickly. In particular, I will talk about measurements that are going to use ZDC, which is a 0-degree calorimeter that is very highly integrated in the accelerator. As you can see from these images, we have a beautiful design that we have been working on, which you can see in here in the SketchUp diagram in the upper right, some type of prototype here. This is the real size, at least area-wise, of what we would need for the ZDC. It's a sampling calorimeter, but it has very high granularity. That's the defining feature of this detector. So with ZDC, we have key channels to measure, which are these two. Deeply exclusive meson production of a proton, in which you have a leading neutron at 0 degrees or very close to 0 when T is small, and a pion in the final state, or you can have a kaon in the final state and a lambda at very forward angles. So those are key measurements, and they have been studied for a while, and I will discuss at least the lambda in more detail. So why would you like to do this? There are various reasons, and one of them is that in principle, we want to study proton structure at the same time as we do pion structure and kaonic structure, because those three hadrons have different ways of getting their mass, and therefore their structure will be different, and how different they are, we will learn about this at the EAC. So doing those type of reactions. So this is coming from a paper by John and company where they projected what type of form factors they could get for pion and kaon at the EAC. And at the EAC, we will greatly expand the coverage that can be done for this type of measurements at fixed target experiments for the pion on the left-hand side and for the kaon on the right-hand side, which there is no data. Even the yellow here is projected measurements at Jefferson Lab. And there are different models that you can probe with this type of measurement, also compared to lattice. I just learned recently that lattice people are getting these form factors right now, and we will be able to probe that at high Q squared. And that is interesting. More interesting, in my opinion, is what you could do with semi-inclusive measurements. In these semi-inclusive measurements, you're going to basically scatter an electron out of a pion. And you can look at an event display in the middle here that shows you what you might find in the main detector, like jets and electrons. And in the forward ZDC, you're going to see a neutron. So you have a leading neutron event, and you are going to be able to constrain T and use this effective scattering as a scattering of a pion target. And we will be able to measure the structure of the pion. But in order to do this with lambda, it's more complicated. Actually, the yellow report, EAC yellow report, states that this is one of the most challenging measurements. And one of the reasons is lambda likes to decay, to fly before decay. And in particular in high energy, is boosted in the lab frame. And so the decay point of lambda that, let's say, was produced at the interaction point can be tens of meters. And you can have at the end a neutron and 2 photons coming from the decay channel, branching ratio of about 30%, where you have a neutron and 2 photons from a pi 0. Those might end up in the ZDC. But the main difficulty is because you have this displaced vertex, and that messes up your ability to reconstruct the mass. So we've looked into this, exactly how we might be able to do this. This is the geometrical acceptance for this decay. On the left-hand side, you see the expected lifetime in terms of meters away from the interaction point. This depends on energy. When you have 100 GeV, it's a steeper curve than when you have 200 GeV, simply because of the boost. Okay? So the higher the energy, the more complicated the measurement it is, because it's further away from the beam pipe. And but for the ZDC case, that's the opposite. If you were to measure this in the charged hadron decay, when you have a proton and a pion, you would like to measure this at low values of Z, because the detector that you would use to measure that is like at 5 meters. So you lose most of the event. But in the ZDC case, we can go and have better acceptance at larger values of Z. That's actually better for us. The closer the lambda is to the ZDC, the better our solid angle coverage. So we projected how well we could do this. So this is the geometrical acceptance if you integrate it over Z for a lambda of PT0 and different colors are representing different PT intervals. So this shows you that even for a PT0 at 100 GeV, you can have like 5% acceptance, which is okay. Then this grows at high energy, and the higher the energy you go, you have higher range in PT. So this measurement, just from the pure geometrical acceptance point of view, is feasible, but it gets messy when you simulate the real signals that we are going to see. And this is what this picture is showing you. These are 3 lambda events at different energies. This thing that is on the front is like a pi0 signature, and the messy thing at the back is the signature of the neutron. And you need to disentangle that. If you run a clustering algorithm, you see the second row color-coded so that the neutron candidate is in green and the other candidates from the pi0 are in different colors. So because this is a very high granularity detector design, we can disentangle these things and measure the lambda. The main issue, though, is to identify what is a lambda and what is a pi0, because these nice event displays that I showed you are just illustrative purposes, but of course, as you can imagine, this can get messy and your photons can start merging with the neutrons. And so your algorithm needs to be good, but we designed that basically with the shower shapes. And the main challenge that remained after you identify neutrons and photons is to reconstruct the Z distribution. Very difficult. How do we do this? We use the fact that we know the mass of the pi0, and we can do an iterative algorithm, changing the assumption of where the position of the decay vertex is, and recalculating the mass until we get the right mass. If we do that, we are able to reconstruct the Z distribution. So this is the truth versus reconstructed Z distribution. It's a nice diagonal, which allows us to measure a nice peak. So this is our simulated events. If you see the blue distribution after our tricks, gives you the invariant mass of the lambda exactly where it should be. And so this really shows, for the first time, that we are able to measure lambda at very high energy with the ZGC. And that is good, because it will open up lots of physics studies. The performance we get for this is good. So this is what the yellow report requirement was in the blue dotted line. And this is the performance we're getting for the theta resolution. So much, much better. And the transverse momentum resolution is shown on the right-hand side for both lambdas and for neutrons. And we are much better than what the intrinsic resolution that will come from the beam divergence effect is, which is shown in the different lines. So at the end, we are not going to be limited by detector effects. So I will just finalize by showing you what type of measurements we could possibly do with lambda. There is a paper by Kong 2 who proposed to do this type of measurements where you have k in the final state and a lambda in the forward direction to understand the phenomenon of spontaneous polarization of lambda, which I will show you in a second. So there are 2 scenarios. So data for a spin. So first of all, I just want to remind you, I'm pretty sure you're aware, but let me just remind you that for the lambda case, you can measure the polarization by looking at the neutron angle in the center of mass triangle. So it's a weak decay that allows you to measure the polarization of lambda. And when people did that in proton-proton collisions and in electron-proton collisions, etc., they observed that the polarization is not zero. It's actually negative, and is a large number when you go high in the fraction of momentum that is carried by that lambda. If you extrapolate to what you would expect at the EAC with deeply exclusive meson production, you get about 60% polarization. So if this thing is the case, like just extrapolating from proton-proton data and electron-proton data from HERA, you expect a polarization of 60% negative in the production plane, which is defined with this cross product. There is another hypothesis that the lambda is really getting the spin from the proton spin. This is the scenario which is called the spin transfer. And in the spin transfer's case, you expect about a 50% polarization. Why, you might ask? The reason is very simple. You get a proton that is 70% polarized. That's just from the EAC specs. And then the lambda carries most of the quark content of the proton except the strings. So you can estimate what polarization dilution you will get, and you get a 50% dilution. There are physics models that are on this case, explain this case, and there are physics models that explain that case, but both cases cannot be right. It's either one or the other. And we're going to measure that. So how are we going to measure this? Well, I don't think anyone thought about this before, but with the ZDC, we have such a good angular resolution that we can do this. So in order to do the spin polarization of lambda, you need to measure the neutron in the center of mass frame. So you take the neutron like an event that looks like this, you boost it to the center of mass frame, and then you look at the angle of the neutron that is going to be modulated by this polarization strength. And that's a way that you're going to be able to do the polarization of lambda. And we tested how well we could do this with our simulations. And it turns out that the resolution is actually super good at the level of 100 microns or so. So this measurement is possible. So this type of new measurements with lambda self-polarization measurements are going to be able to be done. So, and moreover, we're going to be able to do these kaon target measurements, where you have an electron jets in the final state of the main detector and a lambda in the forward direction. So I think that's pretty exciting, because we are going to do DIS of a kaon target. And of course, we have the entire trifecta, where we are going to do jet tomography of the proton, jet tomography of the pion, and jet tomography of the lambda. And we are going to learn about their structures and infer mechanisms by which they get their mass. So in summary, we have planned experiments at Jefferson Lab, which we are going to go in a big fission expedition. And the second part of my talk was about the EAC lambda measurements that are going to give us some new handle on spin too. That's it. Thank you.
So if you go on a fishing expedition, you usually hope there are some fish, right?
Yes.
And so, naive question. So if I take the naive old picture of the EMC effect, where I say, well, for whatever reason, I put a nucleon in the nucleus, and then the structure function within the quark distribution within the nucleus gets changed by whatever, 20-30%.
Yes.
If I take this simple picture, what would I expect for the spin? Also a drop in this naive, very simple picture, or is there an expectation?
Well, it depends, because in that expectation, you are either assuming that all the nucleons are modified the same,
Yes,
like the mean field, and they have their own set of predictions. Actually, they predict a different EMC effect, also big, probably bigger, depends on the kinematics, but let's say bigger in general, a bigger deviation from unity. Okay, that's what they predict. The mean
for the
field
spin, then for
the spin analogous
okay.
EMC measurement. And then there is the other type of measurements where they say only the short range correlated pairs are the ones that are modified, and only those are modified, and they're modified a lot. And those are not predicting a huge effect.
Can you go back to your plot with the curves. So if I remember correctly, though it's been a while, I think there was one labeled NNM, which is some version of a naive, no explicit nuclear effects, but conventional things. And if I remember correctly, the idea with correlation is if you have these high momentum, they're deuteron-like pairs, you basically suppress the polarization in that region. And in general, you get not much effect, but I suspect that like the green and the yellow curves are those because if you get to high X, then you bias towards high momentum, and then you get a big suppression of the polarization. But over most of the region, you get something much smaller. So that these are really sensitive to the shape, not just the size.
Yeah, I know for a fact, I should have said this, but the blue is representative of the mean field. And the blue is, 0.8.
Okay.
For both. So yeah, we do have, like, even naive nuclear effects will give you a deviation from unit.
Okay. So there might be some fish in the pond.
I hope so, yeah.
I think there's somebody online, right?
Well, can I say one other thing just on this? Because the reason I mentioned this high X, that's a piece that stands out, is it goes back to what Spencer asked about earlier, is in a first pass like this, you just define any difference from your free proton as a nuclear effect. And then you have to figure out what they are. But this is one where you've got a couple different approaches, and you do see very specific differences between one approach and another. So while even with the CIS, you'll do the measurement, you'll get a result. You can't instantly say what it is, but there are things like this where you might expect.
I think what you're saying, probably if I'm interpreting you correctly, Jen, what you're saying is, you tell me whether I get what you're saying, is that there are like known effects that you should expect, just like in the EMC, the Fermi motion shoots up at high X, and presumably those type of nuclear effects or some others are also showing in these ratios, the spins, right? Is that correct?
It's that, but also, even though there aren't a lot of predictions for like the CIS, I think when you get predictions, you will probably find certain models will give you very different effects that are indicative of like the broad physics as opposed to the specific model.
Okay.
So that's why I highlight that high X behavior as something that stands out there.
Yeah.
But I'm only going by memory that those are the right models. Sorry, Barbara, went on a while.
No, that's okay. I want to follow up on the fish. So the answer to Volker was yes, there are some fish. So I want to better understand what kind of fish. Can you go to, I think it's slide 26? Maybe 27. One with some data on it. It was, yeah, okay. So there we go. That's a good one. So you see the nuclear effect there, and they're more broadly distributed in transverse momentum than in a proton. That makes sense to me, right? Because you have interactions and exchange of energy that holds the nucleons bound. So presumably that's going to broaden the momentum distribution. Now what happened? You showed one that there was a pretty, there. No, keep going. So keep going, please. Yeah, that. Okay, so you had the dipions, which were a little bit confusing. And I was wondering, so how do we make physics out of these widths? I guess it's the next one I had in mind.
Yeah, that's a good question. So if you were able to interpret this data in terms of quarks and their PTs, the transverse momentum, then this width would be sensitive to that, just like the PT of a single hadron is sensitive to it. Like when these people did when these people here took the single hadron data, they took the PT distribution and they inferred this, that the quarks, their PT is broader, the PT distribution of quarks is broader. If you take the same picture and then you do look at the dihadron channel, you expect the dihadron correlation to also be sensitive to the transverse momentum of those quarks.
So it should broaden.
It should broaden, yeah. It should broaden, and it should be, in principle, a different channel that if there is an ideal world, they are probing the same physics. So you should be able to probe the same transverse momentum dependent PDFs. Now, it's more complicated because in the dihadron case, you have a more different, you have a different cross-section, basically, factorized. It might not be even factorized and to the same degree than the single hadron. But that's the type of things that we are hoping you can expect from the dihadron case. And what type of physics in the fishing expedition, just like in a sentence, without any observer or anything else, it would be interesting to see whether you can discuss anything about spin orbit of the quarks inside the nucleus. Presumably, you have the quarks that are polarized in the proton. When they are polarized inside the nucleus, they are not just going to be standing still. So it's like an orbital motion. So the spin helicity will translate into a spin motion. So I think that would be interesting and might be measurable.
And I had the same kind of question for the case where you showed that in the proton, the spin of the pion and the remnant were anti-correlated.
Yeah.
Makes sense to me somehow. But then, and then in the nucleus, the expectation, the next slide, it was 36, not 26, I'm sorry. Okay. So then what happens if you actually are recoiling against a nucleus rather than just a nucleon, then everything gets scrambled up by the nucleon-nucleon interaction? Is that what makes the projections for the nuclei?
The way that I thought about it, maybe it was naive, but I thought we would fundamentally get the same answer, the same process that you see here for the proton. So you would have this remnant of the proton that is your recoil, and that thing is going to cascade through the nucleus. So you're going to see whether that survives at all. That, let's say, what you call anticorrelation, or what can be called entanglement, whether that survives the nuclear cascade. So I think that the fundamental process would be in the nucleon, just like it just happens that nucleon is going to be embedded in the nucleus.
Yeah, but in the multiple scattering that happens in the cascade, that has to mess it up at least to some extent, no?
If it does, then we will see no asymmetry, and then we will learn that that is the case. But it might be not the case. I don't know. I honestly don't know. I don't have a model. But if it washes up, then we will say exactly that. We will say this entanglement was broken by the cascade through the nucleus. We might find that the entanglement survives, at least to some degree.
I see. And there the different size nuclei give you some filter to see how much it can survive.
Yeah. Yes, entanglement sometimes is very robust, and maybe this is one of those cases. Who knows?
Cool.
All right.
Any other questions? All right, looks like no. Thank you very much.
Sorry for
I think
taking
New has a question. New has his hand up.
Sorry, we can't see them. Go ahead, Nu.
Okay. Can you hear me?
Yes. Hello.
I have a question on page 58 about the lambda spontaneous polarization. I have two questions. One is what is the ZDC X coverage?
X.
Do you have
X. What do you mean by
X? The X, because this polarization is XF dependent, right? What is the coverage here from the ZDC?
You mean azimuth? Do you mean
no, it's XF. You see the plot
XF,
and XF?
yeah, sorry.
Correct.
I didn't
Yes.
Get that. Yeah, that's a good question. I think we can go. To answer that question, I will give you. Excuse me. This one. I don't have it. Well, maybe you can get it here. I can have it here. So you see that at 100 GeV, and the XF will be, it depends on the beam energy, but let's say the beam energy is 250. You do have some acceptance with half XF of 0.5, but it's not a lot because that's the blue curve. We only pick the ones that are close to the CDC. We are much more sensitive to the ones that are XF closer to 1.
Yeah, so the related question is that there have been some measurement in a fixed target experiment about lambda spontaneous polarization. What is unique here in the EIC? I mean, will we get the answer, the source, the cause of the polarization?
I think we have a good shot for various reasons. This is argued in this paper, but I will try to make it justice. So in this particular channel, you only have a kaon and a lambda, and that's it. Okay, so there is no complication about whatever else. So it's exclusive, has that nice feature. So there are no feed downs, for example, that can produce lambda.
Okay.
And moreover, you get XF, which is very high. And so the signal will cover a region that cannot be covered with proton-proton collisions, for example. As you can see on the left-hand side, the plot, the EIC will go right to 1, maybe a little bit below 1. So that maximizes the signal too. So I guess the answer is that the production mechanism is a lot cleaner, so you will get one answer or the other and no competing processes.
Right. When I read this paper, I thought if that's the case, we should go to low energy because this channel is just like associated production. And you constrain both lambda and K plus. That may be much easier measurement-wise. So I have not had chance to talk to.
You mean low energy, like in fixed target electron scattering?
No, just PP collision. PP goes to P lambda K plus. That's much easier. And measurement is also quite straightforward. We can actually even scan from threshold to a little bit high energy to the pair production level.
Okay, yeah, sounds interesting. I'm excited. That's what I can tell you.
But perhaps the measurement just at the XF equal to 1 is not enough. We need some range to see the dependence. That's also what I feel. Yeah. Okay. Thank you.
Okay. Thank you. And sorry for taking too long.
Not at all. All right.